Hi. Okay. So this is one of the chapters of Unit 2. Okay. The name is Photoelectric Emission. Okay. Or you can just call it photoelectric effect also. Okay. This is about how a metal can be charged just by shining a light on it. Okay. With the help of photons. Now, what are photons? I'll explain them to you eventually. Now, so all you have to know are the photons are the light particles. Photons are light particles. It's written over here. What are photons? Photons are light particles in a simple language if you want to know. So, a bundle of electromagnetic energy. This you have to bahar the whole line for unit 2. In examination, they do ask you what are photons? Photons are light particles. Now, what does these particles do? We imagine light to be a complete wave, right? So from where this particle came? This all the questions will be answered later on. Okay. The first thing you guys are supposed to know is that let's say if I have a plate, if I have a plate, a metal plate, and I can charge it either by rubbing it, yeah, or I can charge it, okay, without rubbing it. Like I can remove the charge without even touching the metal. How? With the help of shining, let's say, UV lights. Okay, let's take an example of normal light also can be done. With normal light also you can charge the metal, but it all depends on the metal. Some metal with normal light gets charged. How do they get charged? And you guys know from your O levels and all, how does a metal gets charged? When they lose or gain charges, like electron. If they gain electron, they become negatively charged, and if they lose electron, they become positively charged. So here, if let's say this particular metal has a lot of electron in it, okay. So what we can do is, if we shine any light, if any light particles, that is photons, okay, light particles, that is photons, incident on the metal, if it's incident on the metal, okay, if any light particle incident on the metal, what does the photons do? Photon supplies energy to this electron, and when these electron get sufficient energy, they can get ejected from the metal. They get ejected from the metal, and if they don't get sufficient energy, they stay over there. But if they get sufficient energy, they get ejected, okay. Because of this ejection, now this particular metal is positively charged, okay. I can charge this metal without even touching it with the help of light. It could be any light, but as I said, not all the metals gets charged with the help of normal light. Some metals need higher frequency light. Why? We will see these things later on. Okay, so first of all, we have to know what is a photoelectric emission. It's like when you emit an electron with the help of photons. What are photons? Light particles. That's what they said over here. So let's read the first line. Photoelectric emission is a process during which the electrons are ejected from the metal surface, okay, just the way I showed you guys over here, okay. It is ejected from the metal surface by electromagnetic radiation, for example ultraviolet. It could be normal light also, as I said. When light is shown onto the piece of metal, energy contained within the incident light, so whatever energy, for example, this electron was required, let's say 3 joules of energy, and this particular light had an energy of 4 joules, okay. It supplies the 4 joules to this electron, and when electron gets sufficient energy, they eject, okay. So what they said, energy contained within the incident light is absorbed by the electron within the metal, giving the electron sufficient energy to be emitted from the surface of the metal. And when you lose electron, that metal becomes positively charged, okay. So now let me explain something that was not given in this notes. Let me teach you guys regarding gold leaf electroscope. I hope you guys remember this gold leaf electroscope concept from your O levels. If you don't, please listen to me properly. Now, it's just like a box, okay. It has a metal. The upper surface is metal. Let me change the color. Upper surface is metal, okay. So this is metal over here, okay. And it has this thin gold leaf lines over here, which I'm going to draw right now with the help of brown color. This particular thin, let's say this thin gold leaf is there. It deflects based on the charge of this gold leaf electroscope. What do you mean by deflects based on the charge of the gold leaf electroscope? For example, let's say this particular electroscope is neutral in nature. Okay, it's just neutral in nature. Okay, so it's neutral. You can see the amount of positive charge is equal to amount of negative charges over here. So when you shine light over here, when you shine light, let me take pink. Okay, when you shine light over here, all these electrons, remember the protons don't flow, it's the electron. If the electrons are getting sufficient energy, okay, so these electrons will get ejected, right? These electrons will get ejected, and electrons from here also will reach here and it will get ejected. Okay, so if you draw this diagram again, if we draw this diagram again, okay, let me draw it to some other color. I hope you guys will understand. If I draw this diagram again, you will notice that now since the electron has been ejected, this particular area, everything has become positively charged. So this is positively charged and this also positively charged. You will notice here the deflection is more in this case. Why? Because this is like charges. This is how you know that your light, okay, your electromagnetic waves have, okay, charged the electroscope over here, this gold leaf electroscope. It has charged it. The electron has been emitted. How do you know? If there is a repulsion. Why do you think the repulsion is taking place? Because both of them having the like charges. That is the reason there is a repulsion, because the electron has been emitted from here. And if the electron is gone, when you lose electron, it becomes positively charged. This is one of the proofs, because if you ask me, how do you know the metal is getting positively charged? This is one of the proof experiment to see whether your metal has become positively charged. Sorry, yes, it has been charged or not. Did the electron get removed here or not? This deflection will be more. Now let me teach you threshold frequency. Remember I mentioned previously is that not all the light can emit the electron from a metal. So we have threshold frequency. Threshold frequency is the minimum frequency. It is defined as the minimum frequency of incident light which can cause photoelectric emission. Which can cause photoelectric emission. Okay, so remember, if you shine a light which is less than this threshold frequency, nothing will be emitted. I'll explain you that in diagram. Below threshold frequency, no emission of electron takes place. Threshold frequency is just able to eject the electron. I'll explain them later. First, let me just show you what is the threshold frequency. Like for example, you have metal number 1. Let me draw it in a pink. And let's say you have metal number 2. Let me draw that in a red. So each metal have their own threshold frequency, like minimum frequency. For example, this metals, the electron will only get emitted if you get 3 hertz of frequency. If the light that is coming, if the photons which are coming has a light, this one of 3 hertz, let's say it is 1.5 hertz of light, the electron will not get ejected because it is 1.5 hertz is below than your threshold frequency. Okay, these are for example, these are not constant. Okay, these are just for example I'm showing. So since your threshold frequency is less than, since the incident light, the frequency of your incident light is less than your threshold frequency, no emission of electron takes place. So for example, again I take the same metal right now, let's say 3 hertz. Okay, then electrons, they require 3 hertz of light. So let's say this particular light is having around 5 hertz. Okay, the frequency of this light is 5 hertz. Yes, the electron will get ejected. Okay, electron will get ejected. So remember, threshold frequency is the minimum frequency of light below which no emission of electron takes place. If you have a limit of threshold frequency, you have to have a light which is equal to it or more than it. Even if you shine the light of 3 hertz, the electron will get ejected. But if you do 4 hertz, definitely ejected. 5 hertz, 6 hertz, 100 hertz, the electron will get ejected. But below 3 hertz, no. Because 3 hertz, let's say 3 hertz is the threshold frequency, and below threshold frequency, no emission of electron takes place. Okay. Threshold frequency is just able to eject the electron. Kinetic energy at threshold frequency is 0. It is denoted by work function. I'll let you know. Let me explain this first, then I'll let you know these lines over here, the last 3 lines which I read over here. Okay, so yeah, let's learn about work function. Now, what is a work function? Work function is also similar to threshold frequency. Like, work function is the minimum energy. Work function is the minimum energy. Okay, so threshold frequency is measured in hertz because it is frequency, minimum frequency, and work function is the minimum energy required by the electron before they eject. Like, for example, this electron needs 3 joules of energy to eject. Okay, if the photon that is striking it, is able to supply this electron with 3 joules of energy, the electron will eject, and this is what we call work function. Okay, we can even call it threshold energy, but we don't use that word actually. I don't know whether it will be correct to use that word, but we use the word work function. The symbol of work function is this, I think phi, we call it phi. The symbol of work function, we say it this way. This is how we write it of work function. This is how work function looks like. Okay, and it is the minimum energy. For example, this particular photon has only 2 joules of energy, so the electron will not get ejected because it is less than the minimum energy required. If this particular photon has 6 joules of energy, yes, that time it is double than what is required, so the electron will get ejected. Then you can ask me, what will happen to that extra energy? Because for it to eject, it needs 3 joules. Yeah, for it to eject, it needs 3 joules of energy, but it's getting 6 joules of energy. So is it required or not? So what happens to the 3 joules extra which we are getting? That extra energy, okay, from 6 joules, 3 joules is subtracted by work function. Okay, 3 joules. Okay, now rest 3 joules are left. This rest 3 joules are gets converted to kinetic energy. So remember, for example, if you have this electron and it needs 3 joules of work function, that is minimum energy, and if a photon supplies it with only 3 joules, the electron will just eject. It will just eject, but its kinetic energy will be 0 because there is no extra energy left. Okay, but instead of 3 joules, you supply it with, let's say, 6 joule, it will eject. Okay, also it will have a kinetic energy of 3 joules. That means its velocity is going to be very high. Okay, if you supplied just threshold frequency, the electron will just eject. Work function. Okay, threshold frequency means work function. I'll tell you what is the meaning of that. Threshold frequency actually means kind of work function that I'm going to say you later, but for the timing you have to know, if the photons, okay, if the photon has energy equal to work function, the electron just ejects, but its kinetic energy is 0. But if the photon is having energy more than work function, okay, the electron will eject, yes, but it will move at very high speed also, because it has what? Extra 3 joules of kinetic energy in this particular case. I hope you guys understood this. So let me read this. They wrote, it is the minimum energy. Okay, I don't know why this is not coming. Okay, it is the minimum energy required to remove an electron from a metal. It is a minimum energy. It's measured in joules. Surface. Below this energy, just like threshold frequency, below threshold frequency, no emission. Below this energy, below work function, no electron is emitted. If the energy of the incident light is more than work function, that means if the frequency is more than threshold frequency, okay, so I'll tell you why is this, that I'm going to say you later on. How is the threshold frequency and energy related? Remember, energy is a constant. This is known as Planck's constant. Okay, energy is constant into frequency. This shows that energy is directly proportional to frequency. So that means if frequency increases, your energy also increases. Okay, so remember that at threshold frequency, the energy of the photon is work function. Remember this. At threshold frequency, energy of the photon, energy of the light is work function. So therefore at threshold frequency, now we will understand what is the meaning of this. At threshold frequency, you can just eject the electron. Why? Because you only have work function. That's it. You have the barely minimum boundary energy. You don't have any kinetic energy. Kinetic energy at threshold frequency is 0. It is denoted by work function. I hope you guys understood. You have to know that energy is directly proportional to frequency because this is constant. This is known as Planck's constant. It has a value. I'm going to mention the value later on. So the extra, now what I was saying, that if the energy of the incident light is more than work function, if you supply more than work function, that means if your frequency is more than threshold frequency. So remember, if frequency is more, your energy is also more. So when your frequency is more than threshold frequency, your energy is more than work function. Then the extra energy gets converted to kinetic energy. It is denoted by the symbol phi. Okay. Now let's continue to next. Okay, so I was talking about Planck's constant. Remember, Planck's constant, we use Planck's constant mostly in this formula, E is equal to hf. This means energy is directly proportional to frequency. You have a constant here. What is the value of this constant? This. The value of Planck's constant is given back of your exam paper. Okay, it is denoted by a symbol h. Okay, now all this concept we studied over here regarding emission of electron. Okay, let me rub them and I'll start saying you guys some important points regarding this. What are the important points? Okay, these are some bullet points that you guys are supposed to remember. Remember, energy, I just mentioned this, energy of the incident light depends on its frequency. If the frequency of the light increases, energy of the light also increases. Energy is directly proportional to its frequency. More the frequency, more the energy of the light. However I made the notes. This all three means the same, but you can say it in a three different manner. That's why I wrote this over here. Okay, this formula you guys already know now. Energy is equal to Planck's constant into frequency. Okay, remember, this is a very important point and it is repeated again and again in mark schemes. One interaction between photons and electron is allowed. One photon can transfer energy to a single electron only. Many photons cannot transfer the energy to single electron. What do you mean by this? So remember, let's say you have electrons over here and you have photons hitting. Let's say you have photons, that incident light hitting the electrons. Remember, one photon can transfer its energy to only one electron. Multiple photons cannot transfer energy to a single electron. For example, if an electron requires, let's say, 5 joules, okay, that one single photon should have 5 joules or more than 5 joules. It can have 6 joules, 7 joules, but minimum it needs 5 joules, right? Work function. This is the work function. You need to have equal to work function or more than work function if you want an electron to eject. But let's say this guy has only 1 joules. So we're saying, okay, we can just hit the electron with 5 1 joules electron. 1, 2, 3, 4 and 5. So the electron will get ejected? No, that does not happen. One single interaction is only allowed. That means that particular photon should have energy equal or more than work function. Otherwise, no emission of electron will take place. See what I wrote over here. One interaction between the photon and electron is allowed. One photon can transfer energy to a single electron only. Many photons cannot transfer energy to a single electron. This is just like, let's say I'm supposed to get money from you guys. Let's say one of you, let's say 5 real, and 5 of you said, okay, bhaiya, we will pay 1 real. Okay, we will pay 1 real, you will get your 5 real. But I will, no, I need 5 real only from that guy. You guys will not chip in. This is just like that. Only one interaction. There was a deal between me and him. You guys are not involved. So one photon can emit only 1 electron. Remember that. One photon can emit, okay, according to this, one photon, okay, can emit 1 electron only. Okay, 5 photons cannot emit 1 electron. only one photon can emit one electron. Okay, now what is this? If the intensity of the light is increased, if the intensity of the light, what do you mean by intensity? You guys know what is the meaning of intensity, right? Okay, intensity means, okay, the number of photons that is hitting. Like for example, I have two plates over here. Okay, let's say I have two plates over here, plate number 1 and plate number 2. So if I'm drawing the rays, this is my plate A, this is my plate B. Can you see the intensity of plate B is more than intensity of plate A? Because in plate A less photons are there, less photons, because less intensity. If your intensity is less, number of photons are also less. So in this particular case, if emission is taking place, there will be only 2 electrons emitted, because you see number 1 photon, number 2 photon, so 2 electrons are getting emitted. But in this case, if emission is taking place, 4 electrons will get ejected. 4 electrons will get ejected. Understood? Okay, so 4 electrons are there. So remember, if intensity increases, number of photon also increases. If intensity decreases, number of photons also decreases. So if your intensity is more, if the intensity is more electrons gets emitted from the metal plate. Okay, so if the intensity of the light is increased, the number of electron emitted increases. Why? Because now more number of photons are interacting with electron. More number of photons are interacting with electron. How many photons are interacting over here? 2. How many photons are interacting here? 4. Understood? So how many electrons are getting emitted? Since 2 photons are interacting, 2 electrons will get emitted. How many photons are interacting here? 4 photons. So 4 electrons will get emitted. Why? Because this one's intensity is high. High intense light eta. This one is high intensity. This is low intensity, low photons. High intensity, more number of photons. So remember, intensity increases number of electron emitted, but does not affect the energy of the electron. I already mentioned to you guys that the energy of the electron gets affected by the what? By frequency. So for example, in the previous one, actually let me go to the previous diagram. In the previous one, both the lights were 3 Hertz. Okay, both the lights were 3 Hertz, for example. So they both had the same frequency. Since they both had the same frequency but different intensity, this one's intensity, plate B's intensity was high and plate A intensity was less, but they had the same frequency. So that means both electron from both the plates will eject at same speed. So remember, the kinetic energy of both the electron from both the plates is not getting affected. Only how many electrons is getting emitted, that is affected. Remember, intensity only affects the number of electron. It does not affect kinetic energy of the electron. It does not affect at what speed the electron will eject from the plate. At what speed the electron will be ejected from the plate will depend on the frequency of the light. If I increase the frequency of the light, the electron speed is going to increase. I already told you, because energy is directly proportional to frequency. So if you increase the frequency of the light, the electron is getting extra energy. That extra energy gets converted to kinetic energy. So let me show that to you over here. If the frequency of the light is increased, they wrote there. If the frequency of the light is increased, then the kinetic energy, that means the speed of the electron, gets increases, but it does not change the number of electron emitted per second. So remember I have 2 plates here. Plate number 1, let's say 3 photons. Here also 3 photons. Okay. So can you see the intensity is same? Because the number of photons are same, so therefore intensity is same. How much electron will get emitted? 3 electron will get emitted. For example, this is 3 Hertz and this is 5 Hertz. Okay. So can you see this one is more frequency than this plate A? Plate B has more frequency than plate A. So the electron here in this region will have less speed when it ejects. It has less kinetic energy. Why? Because it has less frequency of light. But this one is high frequency of light. The number of electron emitted is 3 only, because intensity is same for both of them, both the plates. But the speed at which those electrons are getting emitted is differing. Why? This one has more frequency, so its kinetic energy is going to be more, so its electron will eject at higher speed. All 3 electrons will eject more speed, or it will have more kinetic energy compared to these 3 electrons. Intensity decides number of electron, frequency decides what is the at what speed will the electron eject. Okay, let me repeat again. The number of electron ejected, number of electron will depend on intensity. If you increase the intensity, number of electron ejected will be increased, but the speed of the electron won't change if you don't change the frequency. Let's say you change the frequency, okay, but you kept the intensity constant. If you kept the intensity constant, okay, your number of electron ejecting will be same, but the one with the higher frequency will have more kinetic energy. Okay, now this is the equation of photoelectric emission. Let me explain this to you. Okay, let me explain this to you. This shows that the energy of the light, okay, the energy of the light, that is HF, okay, is equal to, okay, sum will taken by the work function, okay, sum is used to eject the electron, because you need minimum this thing na energy to eject the electron, so some energy will be taken by this thing, rest all the energy will get converted to half mv square, that means kinetic energy. So if you really want to write this equation, this is how it looks like. E means HF, E is equal to phi means phi, and kinetic energy, our kinetic energy you mean is half mv square. Okay, so you can actually see the equation. If you rearrange the equation, kinetic energy is from E, from your total energy of the light. Remember, this is the energy of the light. From the total energy of the light, how much of our work function has been cancelled, the rest of the energy gets converted to kinetic energy. I hope you guys understood this part. I'll explain this graph. After this graph, the first video will be over. So what is this graph? What they did was, they did an experiment where they increased the frequency of the light, and they saw what was the kinetic energy of those electrons, and they got a straight line. It's not from the origin, this is the straight line they got. And if you draw a kinetic energy versus frequency graph in the examination, they will give you till here. Okay, this is known as threshold frequency, because you see, this is the frequency at which kinetic energy is 0. I already told you over here that at threshold frequency kinetic energy is 0. See, threshold frequency is just able to eject electron, kinetic energy at threshold frequency is 0. So wherever, if you draw a kinetic energy versus frequency graph, wherever your graph crosses the x-axis, that is your threshold frequency, because your kinetic energy is 0. You can see, as you increase the frequency, your kinetic energy increases, but at threshold frequency kinetic energy is 0. In the examination, you have to extend this line with the help of a ruler, and you have to see where it is cutting the y-axis to find the work function value. Now, and if you want to find the Planck's constant, you have to find the gradient. If you want to find the Planck's constant, you can find the gradient. Okay, so you have this work function over here. Check this work function. Y-axis, cutting y-axis, work function. Cutting x-axis, threshold frequency. Gradient, slope. But why? I already explained this here with the help of y is equal to mx plus c. Let me still explain it to you. Okay, so you can see this is the equation, right? This is the equation we are using the graph. Kinetic energy is your y, because we are drawing y over here. See, at y we are having y-axis, we are having kinetic energy. Okay, then you have phi minus hf. Instead of E, I have to write hf. Instead of E, I have to write hf. Okay. Okay. So frequency is my x-axis. This is my x-axis. So this is my gradient. So hence proven, the gradient of kinetic energy versus frequency graph is Planck's constant. Okay. And y-axis, this is c, right? This is c, right? C means wherever it crosses the y-axis. So y-axis is work function. I hope you guys are able to understand this. Okay, I'm ending this video here. I will make part 2 later on.